Welcome back to Mental Math. Here's an equation that might look like someone made a typo. 1 to the power of x equals 12. Now, this seems completely impossible at first, but it actually holds a beautiful secret about how numbers really work. Our job today is to solve for x. And honestly, your first instinct might be that there are no solutions whatsoever. Let's start by thinking about this in the familiar world of real numbers. You know, the numbers we deal with every day. But wait, let's actually think about why 1 to any power equals 1. This isn't just some arbitrary rule. When we say 1 cubed, we mean 1 times 1 times 1. And since multiplying by 1 doesn't change anything, we get 1. 1 to the 100th power is just multiplying 1 by itself 100 times. But no matter how many times you multiply 1 by itself, you always get 1. Even for negative powers, 1 to the negative second is 1 divided by 1 squared, which is 1 divided by 1, which is still 1. And fractional powers? 1 to the 1/2 is the square root of 1, which is 1. So indeed, in the world of real numbers, 1 raised to any power is always just 1. This is because 1 is the multiplicative identity. It doesn't change anything when you multiply by it. And since 1 is definitely not equal to 12, we've got what seems like a fundamental contradiction. So there are no solutions for x anywhere on the real number line. But here's the thing. This isn't the end of our story. To actually find a solution, we need to venture into a much richer mathematical universe, the complex plane. The first key insight is Euler's identity, which is genuinely one of the most beautiful formulas in all of mathematics. It connects the exponential function e to trigonometry through the imaginary unit 1. So what exactly is the number 1 when we're thinking in the complex plane? Turns out it's way more than just a single point. The number 1 actually represents any integer number of full rotations around the origin. For any integer k, the cosine of 2 pi times k is 1, and the sign is 0. Using Euler's identity, we can now express 1 in this really powerful exponential form. So 1 equals e raised to the power of I times 2 pi times k, where k is any integer. This is the first piece of our puzzle. The second key insight is understanding logarithms in the complex plane. Unlike real logarithms, complex logarithms are multi-valued, which reflects the periodic nature of angles. Just like with the number 1, we need to express 12 in its full complex form. The number 12 has a magnitude of 12 and an angle of 0, plus any integer n number of full rotations. This gives us 12 times e to the I times 2 pi times n. All right, now we have everything we need to actually solve this equation properly. Let's start again with our original equation. Now we replace both 1 and 12 with their full complex exponential forms. This substitution reveals the true structure of what's going on. On the left side, the usual rules of exponents still apply. We can multiply x into the exponent, and this cleans up the left-hand side. Now, to isolate the term with x, we need to undo this exponential function by taking the natural logarithm of both sides. So we apply the natural logarithm to both sides of the equation. On the left, the log cancels the exponential. On the right, we use that logarithm property where the log of a product is the sum of the logs. This breaks the right side into two much more manageable terms. And again, the logarithm and exponential cancel each other out. Now we're left with a much simpler linear equation for x. Finally, to get x by itself, we just divide both sides by the coefficient of x. And this gives us the complete, though not yet simplified, solution for x. We have the solution, but we can write it in a more standard and elegant form, a plus b times I. Starting with our result, the first step is to separate this fraction into two parts. We can split the numerator to create two separate fractions with the same denominator. This nicely isolates the real and imaginary components. Let's focus on the second term. We can cancel out the common factors of I, 2, and pi. This simplifies to just n over k, which will be the real part of our solution. Now for the first term. To remove I from the denominator, we multiply both the numerator and denominator by I. This moves I to the numerator and gives us I squared in the denominator. By definition of the imaginary unit, I squared equals -1. Substituting -1 cleans up our first term. Finally, let's rearrange the terms into standard form. Real part first, then the imaginary part. And here's our final, complete, and beautifully structured solution for x. Now, this isn't just one answer, it's an entire universe of answers. Remember that k and n can be any integers, but k cannot be 0, since that would cause division by 0. The real part of our solution is n over k, which can be any rational number. The imaginary part depends only on k. Let's visualize these solutions on the complex plane. They form this really fascinating pattern. For k equals 1, the imaginary part is fixed, while the real part n can be any integer. This creates a horizontal line of solutions. For k equals -1, we get another horizontal line mirrored across the real axis. For k equals 2, the points are closer to the real axis and twice as dense. For k equals -2, we see the same pattern on the other side. As we change k, we generate an infinite set of these horizontal lines, which get infinitely close to the real axis. So what's the final verdict on this seemingly impossible equation? An equation that has 0 solutions in the real world has this infinitely rich and beautifully structured universe of solutions in the complex plane. The solutions form a dense set of points, revealing that exponentiation is way deeper than it first appears. This is a perfect example of how complex numbers give us a more complete picture of what mathematics really is. Thanks for sticking with me through this mathematical journey. If you enjoyed exploring how complex numbers reveal hidden solutions to impossible equations, please hit that like button and subscribe for more mental math adventures. Until next time, keep questioning what seems impossible.